So in this video, we are going to be solving a problem to explain the Carnot cycle. Just in case you missed the first video, I've dropped the link of that video in the description of this video, so you can go and watch it for proper understanding. Now this question says, calculate the heat and work transferred, the cycle efficiency, work ratio, and steam consumption of a Carnot cycle using steam between pressures of 30 bar and 0.04 bar. So key parameters here, between pressures of 30 bar, P1 is given to us as 30 bar, and 0.04 bar, P2 is given to us as 0.04 bar. Now we are asked to calculate the heat transferred. That's the net heat. We're asked to find the work transferred, which is the net work, unknown. We're asked to find the work ratio, unknown. We're asked to find the specific steam consumption, unknown. We're asked to find the efficiency, unknown. Okay, so let's start by plotting our TS diagram. So these are pressure 1, 30 bar. So I explained all of this in the first video. Please do well to watch that video for proper understanding. These are pressure 2, 0.04 bar. Okay. So in the first video, I explained that the enthalpy at state 1, this is state 1, this is state 2. Enthalpy at state 1 is H1, and this H1 is equal to HF because state 1 is directly at the fluid line of the TS diagram, or the TS diagram. Now at state 2, H2 is equal to Hg because state 2 is at the vapor line, so H2 equals Hg. But at state 3 occurs at the saturated vapor and liquid phase, which is a mixture of the two. So since it's occurring at this point, we need to find the dryness fraction at this point, labeled as X3. So with this, we can be able to find our H3, which is equal to HF3 plus X3 HFG3. But the problem now is to find our dryness fraction. But the only way we can do that is by employing the isentropic condition that is seen on the board. So state 2 and state 3 is a reversible adiabatic process. If you trace them down, it touches the entropy line. So which means state 2 and state 3 is a constant entropy process. That simply implies that the entropy at state 2 is equal to the entropy at state 3. Now the entropy at state 2, S2, is equal to what? Sg. Just like H2 here is equal to Hg, S2 is also equal to what? Sg. With this, we can be able to relate this equation together. If we know Sg, that's S2, then we can find X3 from there. X3 itself, meanwhile, X3 itself is simply SF3, just basically the same equation but different parameters now, plus X3 SFG3. So from here we can be able to get our dryness fraction, but let's get into it and see. Now, the first pressure is 30 bar. So from saturated water and steam table corresponding to 30 bar, we find H1, which equals HF, and that's going to give us, so we simply go to our steam table now. Let's go to the steam table.
So we'll go to the steam table now, corresponding to pressure 30 bar. So I'm going to be zooming this up a little bit. This is our steam table. This is the pressure line, temperature, volume. So what we are looking for is simply HF, HFG, Hg, SF, SFG, Sg. So if you count from after the pressure, you count 1, 2, 3, 4, 5. You get into the lane of the enthalpy, and the next lane is the lane of the entropy. So now let's trace for pressure. Let's get 30 bar, right? So you go down. I'm going to be zooming up a little bit so that it becomes clearer. So if you go down, this is 30 bar, as can be seen here. So 30 bar, let's count 5 down. 1, 2, 3, 4, 5. So this is our enthalpy. So just to be clear, let's move up a little bit. So you have this to be the enthalpy lane. Okay. So at 30 bar, as can be seen, at 30 bar, enthalpy is 10, HF is 1008. HFG is in between, that's 1795, and HG is 2803. Similarly, SF is 2.645, SFG is 3.541, and SG itself is 6.186. So these are the parameters that we need, so keep them in mind. So that's how you get your enthalpy and entropy from the given pressure. So let's trace down once again to make sure it corresponds to 30 bars. Can be seen, it corresponds to 30 bar.
So corresponding to 30 bar, H1, which is HF, is simply 1008 kilojoules per kilograms. So this is our H1. Also from here we find our H2. H2 is going to be equal to Hg, still under 30 bar. So we navigate to, that gives us 2803 kilojoules per kilogram. Okay, so we have now the enthalpy at state 2, we have the enthalpy at state 1. Next, let's just find all the properties at this point. We can also find the entropy S1. S1 is also going to be SF at that state. So under 30 bar, locate SF, that gives us our X1. So we find SF now. So SF is 2.645. 2.645, that gives us kilojoules per kilograms Kelvin. So we'll also find S2, that gives us SG. S2 is simply SG. So we'll move to SG, which give us 6.186. 6.186 kilojoules per kilograms Kelvin. So these are the parameters at that particular pressure. So we find for 0.04 bar. So at 0.04 bar, so we'll repeat the same thing. Now 0.04 bar is the second pressure. At this point, we'll find the properties of state 3 and state 4. Just like we'll find the properties of state 1 and state 2 at 30 bar. You can see it here, H1, H2, X1, S2. We'll also find the properties at state 3 and state 4 at 0.04 bar. So at 0.04 bar, so what we find at 0.04 bar is now going to be HF3, which is this, HF3, which is this here. So we'll find HF3. This is going to be equal to, so under 0.04 bar from the steam table, locate HF, please. HF becomes HF3 at 0.04 bar. So let's get to it.
So now we locate 0.04 bar. We go to the pressure. This is 1 point, so it's quite high. Let's move up. So be careful. From the pressure, this is 0.40. We're looking for 0.04, right? So okay, so this is 0.04 bar here. This is the pressure line, so as can be seen, 0.04. So remember, you count 5. 1, 2, 3, 4, 5. So this is our HF, right? These are HF. So this HF becomes HF3, 121. This is HFG3, 2433, and this is HG, 2554, and this is SF3, 0.422. This SFG3, 8.051. This SG, 8.47. Sorry, 8.473. Yeah. So if you trace, of course, if you trace up, you're going to see that this is HF, HFG, HG. So this is what we need for the pressure 0.04 bar.
So HF1, HF3 is 121 kilojoules per kilograms. Now we also find HFG. So we'll find HFG3. Okay, Okay, so find HFG. HFG there is under 0.04 bar is 2433. You have 2433 kilojoules per kilograms. Similarly, we'll find for the entropy SF3. Entropy that becomes SF3. SF3 is going to be equal to okay, SF3 is 0.422. So simply SF at that point 0.422 kilojoules per kilograms Kelvin. We'll find SFG3. So SFG3 that gives us 8.051. Of 8.051 kilojoules per kilograms Kelvin. Okay. Now, having found these parameters, we know our H1 and we know our H2. We can compute the heat supplied. Heat is supplied from state 1 to state 2 in the Carnot cycle. So I explained all of this in the first video. So the heat supplied, Q1, is equal to H2 minus H1. So heat supplied is going to be equal to H2. H2 gave us 2803. So you have 2803 minus H1. H1 gave us 1008 minus 1008. So which means our heat supplied is equal to 2803 minus 1008. So this gives us 1795 kilojoules per kilogram. So this is heat supplied into the system. Now between stage 2 and stage 3 is where the expander removes work from the system. The work removed by the expander, called that W1, is equal to, is also a difference in enthalpy. So it becomes H2 minus H3 because that work is positive. You have H2 minus H3. So I explained all of this in the first video. How to even get the formula, please go and watch the first video for proper understanding. Now we know what our H2 is, but we don't know what our H3 is. For us to get H3, we need to find the dryness fraction at that point. In order to find the dryness fraction, the first thing we have to do is to equate the what? Enthalpy. You will recall that stage 2 and stage 3 is an isentropic process. So since it's an isentropic process, it means that S2 is equal to S3. Okay, we can do that there. So I'm taking this off now. So for isentropic state 2 to 3, S2 equals X3, but X3 itself, we found the formula earlier as SF3 plus X3 SFG3. S2 we know the value, we found the value of S2. S2 is simply SG at the first pressure 30 bar. That gave us here 6.186. So you have 6.186 to be equal to, so SF3, we found SF3 from here. SF3 is 0.422. So you have 0.422 plus X3 multiplies SFG3. SFG3 gave us 8.051. So you have 8.051 X3. So from here we can be able to find the dryness fraction at that point. So let's simply send this man over here. We have 6.186 minus 0.422 to be equal to 8.051 X3. So let's find this difference. 6.186 minus 0.422. That gives us 5.764 to be equal to 8.051 X3. So therefore, the dryness fraction at state 3 becomes 5.764 divided by 8.051, which implies that dryness fraction at state 3 is going to be equal to divide 051. So the dryness fraction gives us approximately 0.72. So which is quite correct, because 0.72 is almost 1. At the gas line, the dryness fraction is 1. So 0.71 is quite correct. So this is now the dryness fraction as state 3. With this, we can now be able to find the enthalpy as state 3. Remember, enthalpy as state 3, H3 is HF3 plus X3 HFG3. So this is going to be equal to HF3. We found HF3 here. So our HF3 is 121. So we have 121 plus 0.72 multiplies HFG3. HFG3 gave us 2433 multiplies 2433. So with this now we found enthalpy as state 3. So I'm going to punch everything all together to save time. 0.72 multiplies 2433 plus 121. So H3 gives us 1872.76. H3 is 1872.76 kilojoules per kilograms. Now we know H3, we can now be able to find the work done by the expander. So W1 is equal to H2. Our H2 gave us 2803 minus 1872.76. So the first work done, or work removed by the expander, becomes 2803 minus answer. So this work done is positive because the expander removes work from the system. So you have 930.24. 930.24 kilojoules per kilograms. So this becomes the work done by the expander. So between state 3 and state 4, heat is now removed by the condenser. Between state 3 and state 4, heat is removed by the condenser. So that heat removed is what we are going to be looking for right now. The heat removed is Q2, and that's equal to, since heat is removed, it simply means it's going to be negative. When heat is removed from the system, it becomes negative. So it becomes H4 minus H3. H4 minus H3. So we know what H3 is. Now we need to find H4. In order to find H4, we have to now repeat this process for state 4. State 1 and state 4 is isentropic. With this, we can now be able to find the what? Dryness fraction at state 4, which is X4. We can be able to find the dryness fraction at this point. So let's do that still over here. So for the isentropic state 4 to state 1, state 4 to 1, it means S1 is equal to what? S4. But S4 itself is SF4 plus X4 multiplies SFG4. So it is important to know that state 3 and state 4 operate at the same pressure. So if they operate at the same pressure, it simply means that X3 it means that SF3 is going to be equal to SF4. So this is also our SF4 because they operate at the same pressure. Same thing as SFG. This is also going to be SFG4. It's also going to be equal to this value since they operate at the same pressure. Okay, so just keep that in mind. Alright, so S1, we'll find the value of S1 already. S1 is SF at 30 bar and the value is 2.645. So you come here and plug it. 2.645. This is equal to SF4. SF4 is SF3, which is 0.422. So you have 0.422 plus. Next is X4 multiply SFG4. SFG4 still gave us here 8.051. So this is 8.051x 4. So 2.645 minus 0.422 equals 8.051 x4. So let's find this difference and see. 2.645 minus 0.422, that gives us 2.223 equals 8.051 x4. So from here we can now find the dryness fraction at state 4 to be 2.223 divides 8.051. So let's see what we have. Divide 8.051. So this gives us approximately 0.23, which is logically correct. 0.28 please. 0.28, which is logically correct because state 4 is almost at the liquid line, so it's supposed to be 0. So 0.28, which is logically correct. So we have the dryness fraction at state 4 to be that. So if we know this, we can now plug into the equation to find enthalpy at state 4. Okay, I think at this point I'll take this off. Don't know if I'm supposed to be doing this again, but okay, I've already taken it off. Now, the enthalpy at state 4, H4, is now going to be HF4 plus X4 times HFG4. Okay, I've taken this off. I'm supposed to need it, but it's okay, we can find it. So H4 is equal to HF4 is supposed to be enthalpy at 0.04 bar. So I've cleaned that. Let's look for it again. Enthalpy at 0.04 bar. So that's 121 plus X4, which is 0.28, multiplied by HFG4. HFG4 gives us 2433. So times 2433. So with this you can find H4 to be equal to, so let's do the maths. 2433 multiply 0.28 plus 121. That simply gives us 802.24. 802.24 kilojoules per kilograms. So now that we have H4, we can now find the heat supplied or the heat removed from the system. Q2 is now going to be equal to H4 802.24 minus H3, and we got H3 earlier. Where? Okay, so we can get it here. This is H3. H2 minus H3, so this is H3. 1872.76. So minus 1872.76. So this means that the heat removed from the system is going to be equal to minus 1872.76. So that gives us negative 1070.52. Negative 1070.52 in kilojoules per kilogram. So once again, heat removed from the system is negative, which is why you're having that negative value there. Finally, between state 4 and state 1 is the compressor. Compressor compresses the fluid, adds work to the system, and work added to the system is negative. If work is added to the system, that work is negative. So the compressor work is going to be negative. Alright, so the compressor work is W2. That is going to be equal to, from state 4 to state 1. So it has to be the lower enthalpy minus the higher enthalpy. So H1 is 1008. H4 Okay, I think we already have H4 here. So H4 is 802. So it becomes H4 minus H1. The lower enthalpy minus the higher enthalpy because it's a negative work. So W2 equals 802.24 minus H1 is 1008 minus 1008. So the work removed or the work added by the compressor becomes 802.24 minus 1008. That gives us negative 205.76 kilojoules per kilograms. Okay, so we have everything we need right now. Let's start solving. The first question says we should find the net heat supplied or net heat transferred. Net heat equals the heat from the heater plus the heat removed from the condenser Q2. So this is going to be from the cooler, sorry. So this is going to be equal to heat supplied Q1 gave us 1795. So you have 1795. Heat rejected Q2 gave us negative 1070.52. So minus 1070.52. So this implies that our net heat transfer is going to be equal to 1795 minus 1070.52. That gives us 724.48. So the net heat is 724.48 kilojoules per kilograms. So that's the answer to that particular question. The next question says the network transferred. Network. So the network is going to be equal to the work done by the expander W1 plus work done by the compressor W2. So network equals the expander work. W1 gave us 950.24. 950.24. Work removed by the condenser W2 here is 205.76. So negative, right? Yes, negative 205.76. So minus 205.76. So our network is going to be 950.24 minus 205.76. That simply gives us 744.48. 0.48 kilojoules per kilograms. This becomes our network. The next question says we should find the work ratio. The work ratio is the ratio of the net work to the positive work. The positive work in this case is the expander work. So the net work to the expander work. So work ratio is the positive work or net work to the positive work or the expander work, which is W1. So net work gave us 744.48. W1, which is expander work, and that's the positive work, is 950.24. Divides 950.24. So we have the work ratio to be equal to 744.48 divides 950.24. So that gives us 0.78. So our work ratio is 0.78, approximately 78%. What else? We are asked to find the specific steam consumption. Specific steam consumption, SSC, is equal to 3,600 divided by network in kilojoules, in kilograms per kilowatt hour. So this is equal to 3,600 divided the network is 744.48 divided 744.48. So we'll have this to be equal to 3,600 divides 744.48. So specific steam consumption is 4.84 approximately. 4.84 kilograms per kilowatt hour. That's the specific steam consumption. Okay. Finally, we are asked to find the efficiency of the system. You can do that here. Efficiency is actually network over heat supplied, Q1, multiplied 100%. So the efficiency becomes our network is 744.48, 744.48 divides heat supplied, Q1, heat supply is 1795, that multiplied by 100%. So efficiency is going to be equal to 744.48 divides 1795. So efficiency is approximately 41.5%. Alright guys, so that's how to solve questions in the Carnot cycle. So I will see you in the next video with more amazing questions on Carnot cycle. Please do well to appreciate this video by liking, commenting nicely, share to your friends, and subscribe to the channel. Turn on your bell notification so you don't miss out our subsequent videos when they drop. I will see you in the next video. Thanks.